In this video, we'll learn about VAE, stands for Variational AutoEncoder. It's a type of generative model and advanced version of autoencoder. But why we need it? Because a normal autoencoder learn to compress an image into latent representation and reconstruct it. But its latent space not necessarily continuous or well organized. If we randomly choose a point from latent space and give it to the decoder, there is no guarantee that we will get a meaningful image. This makes the latent space difficult to sample from for genres. How variational autoencoder works. The goal of a VAE is learn to generate a model that assign high probability to the images in our dataset. So how do we maximize this probability? Let's derive it. We have to maximize p theta of x, where x is all present images in our dataset. We take log of p theta of x and then expand p theta of x, and then we multiply and divide q phi of z conditioned on x. By Jensen inequality, log of expectation is always greater or equals to expectation of log. Now we separate x and z probabilities. And z part became Kullberg-Leibler divergence of q phi z condition on x and p theta of z. Maximize the probability of p theta of x, we have to maximize the value of this evidence lower bound, which is consist of reconstruction part and KL divergence part. Get the reconstruction loss, we have to add the negative sign to this reconstruction term. Now let's derive the KL term. We don't know the latent distribution of our dataset images, so we assume that P of Z is a normal distribution with zero mean and one variance. So now we derived loss function for the variational autoencoder. Now we implement VAE by code. We train this VAE by 64 by 64 pixel input and 64 by 64 pixel output, and latent have 256 dimensions. I trained this VAE on 50 epoch, and still generated images are blurry, and it can be improved by increasing the dimension of latent space and more epoch.